Let us recap what we did in the previous lecture. So let me first review the previous lecture. Okay, what did we do in the previous lecture? We talked about the channel capacity of an additive white Gaussian noise channel. So channel capacity of additive white Gaussian noise channel. Okay, and what is the capacity? It is given or denoted by the letter C, and for an AWGN channel it is defined as C equals B logarithm to the base 2 1 plus signal to noise ratio. So that's the capacity of the channel. And then we talked about the Shannon-Hartley theorem, Shannon-Hartley theorem, also called as the channel capacity theorem, which says that if your rate of communication, if the rate of communication R is less than the capacity of the channel C, then we can have reliable communication. Reliable communication with small error probability is possible using some coding technique. Okay, coding. On the contrary, if the rate of communication R exceeds the capacity of the channel C, then no matter which coding technique is used, the error probability will not be small. Right? So that means if we exceed the capacity of the channel, then no matter what technique we use, the error probability is going to be too high. That means there will be too many errors in the received data, and that would make the data basically useless. So it's like, if we compare it, if I give you an analogy, it's like having a speed limit for the road. Okay, so your road has a certain speed limit which is called as the capacity of the road. As long as you're driving at a speed which is below the speed limit of the road, then the chance of an accident is going to be very, very low. So the probability of an accident will be very low. Of course, you'll use some safety mechanisms like wearing the seat belt and other safety features, right? But if you drive at a rate or drive at a speed faster than the speed limit of the road, then no matter how what safety precautions you are going to take, the chance of an accident and hence the chance of an injury becomes too high. The probability of injury is high, even though you might have all the safety features. Just because you are driving above the speed limit, the probability of an injury becomes high. So similarly, on a communication channel, there is something called as a capacity of the channel. And as long as we communicate or transfer data at a rate which is below the capacity of the channel, then we can have a small error probability by using some coding technique. If we exceed the capacity of the channel, then no matter what coding technique we use, the error probability will not be small. The errors will be too much. Now, how do we know the capacity of the channel? Well, it depends on the type of the channel, and here we are focusing on the additive white Gaussian noise channel in our course. So for the AWGN channel, the capacity is given by this equation, and in the sense that it depends on the bandwidth of the channel and the signal to noise ratio of the channel. So if you want to increase the speed at which we want to communicate, then we have to increase the capacity of the channel by either increasing the bandwidth or increasing the signal to noise ratio. And we have seen in the last lecture how we can increase the capacity and what is the effect when we increase bandwidth, because increasing bandwidth has a direct effect on the noise power, because the noise power depends on the bandwidth. So if you increase the bandwidth, the noise power is going to increase, and therefore for a given signal power, the signal to noise ratio will decrease, and so on. So we discussed all of these things in the previous lecture. And then we started off with channel coding. So because the whole idea here is that we can have a small error probability by using some kind of a coding technique. So we started off with some basic coding technique. So we call these as channel coding. And in this, the first type of channel coding technique that we saw was a very basic one, which is called as the parity code. So we discussed what is a parity code in the previous lecture. So in parity code, we have some bits which are called as the information bits, and to the information bits we add a single bit of parity bit. So we call this as the parity bit, and after adding the parity bit by following some rule, we combine the information bit and the parity bit, and together that is called as a code word. And in the parity codes, we talked about two types. We talked about even parity, and we also talked about odd parity. Right? We did these things in the previous lecture, and we also made some definitions related to the coding schemes. So let me just give an illustration again, just to recall the even parity. So similarly, whatever we discuss here for even parity, it applies to the odd parity as well. I'm not going to do both because I've already discussed that in the last lecture. So for even parity, suppose we have one information bit. So the information bit is either 0 or a 1. So to this information bit, we add a parity bit. The parity bit for even parity is added in such a way that the total number of ones in the entire code word after adding the parity bit is even. So for 0, we want to add a parity bit such that the total number of ones is even. So this has to be 0. So 0, 0. So the total number of ones in this case is 0, which is an even number. And for if the information bit is 1, we have to add the parity bit in such a way that the total number of ones becomes even. So therefore this would become 1. So in this case, we have one information bit and one parity bit, and we've added the parity bit in such a way that the total number of ones in the entire code word is even. So we have 0 ones here, and here we have 2 ones. So the number of ones is even. That's why we call it as the even parity. In this case, we define the number of information bits, which we call as k. So k is the number of information bits. In this case, this is equal to 1. N is called as the block length, or the length of the code word. So the total length of the code word in this case is 2, right? So the total length is 2, and out of the 2 bits, 1 bit is the information bit and 1 bit is the parity bit. So the number of parity bits is given by n minus k. N minus k is the number of parity bits, which is equal to n is 2 and k is 1, so 2 minus 1 is equal to 1. And what is the code rate? Code rate. We defined the code rate in the last lecture R to be equal to the ratio of the number of information bits to the block length, which is k by n. In this case, it is 1 by 2. and if we write that as a percentage, that gives us the coding efficiency. So which is equal to 0.5, or we simply say the coding efficiency is in this particular example 50%, where we have for every bit of information we add one parity bit. That means for every bit we are adding one protection bit. So this extra bit that we are adding, it is not part of the information, so for the end user that will be discarded, but the transmission cost includes the cost for transmitting both the bits. So out of 2 bits, only one of them is the useful bit for the end user. So the coding efficiency is said to be 50%. And whenever we design any coding technique, the objective is to have the code rate as close as possible to 1. So the code rate, since for any coding scheme, the number of information bits k is going to be less than or equal to n. That means the code rate r is going to be less than or equal to 1. And when we design a coding scheme, our objective would be to have the code rate as close as possible to 1. That means we have a coding efficiency close to 100%. So the design objective is to have code rate approaching 1, okay, with maximum, let me write that clearly, with maximum error detection or correction capability. Okay, that would be the design objective when we design any coding technique. Now the parity codes that we are talking about now, they are only error detection codes. They can detect errors, but they cannot correct any errors, okay, as we will illustrate a bit later. And let me take another example where we have a higher code rate. So rather than having one information bit and one parity bit, we can have 2 information bits and 1 parity bit. So that would give us a higher code rate and hence a higher coding efficiency. So with obviously the notation that we are going to use here is it's called as an NK code. So in this case n is 2 and k is 1, so therefore this is a 2-1 code. So that means there is 1 information bit and the total length is 2 for the code word. So we have a coding efficiency of 50%. Similarly, now we are going to do NK code, which will be 3-2. So we have 2 bits of information, 00, 01, 10, 11. With 2 bits of information, we have 4 possible combinations. And again, I'm going to do it for the even parity case, even parity. So for 2 bits, we have to add an extra bit now, such that the total number of ones is going to be even. So in this case, the extra bit will be 0. Here, the extra bit, the parity bit is 1. So the total number of ones is even. For this particular information sequence, the parity bit is also 1. So the total number of ones is even in this code word. And here also, here we have already 2 bits, so 2 ones, so we have to add the parity bit as 0. So the parity bits have been added such that the total number of ones is even. Here we have 0 ones, here we have 2 ones, here we have 2 ones, and here also we have 2 ones. So the extra parity bit here is added such that the total number of ones in each code word is even, because we are following the case of even parity. Okay, so that's what we have been talking about. And what is the notation for this? Since we have 2 information bits and 1 parity bit. That means k is equal to 2 and n is equal to 3. So we write this as an nk code, which is in this case 3, 2 code. Right, and what is the code rate here? Code rate is k by n, which is 2 by 3, which becomes 66.67%. So the coding efficiency is 66.67%. So that's the coding efficiency. Okay, so like this we can keep on increasing the code rate. Obviously when we increase the code rate, the efficiency increases, but that also would affect the error detection or correction capability of the coding technique. Now for the parity codes, if you recall, the parity code, let me change my color. Parity codes can detect odd number of errors. So we discussed this in the last lecture. Odd number of errors. That means if the number of errors that are present in a given code word is odd, that is, there is a 1-bit error or 3-bit errors or 5-bit errors, it can detect it. However, if the number of errors is even, then the parity code will not be able to detect it. So it will think it is a correct code word. So it cannot detect parity codes. Parity codes cannot detect even number of errors. So let's have a quick example. So let me take one particular code word. So I'll take the second code word here, 0, 1, 1, and we know that we are following this, we created this code word using even parity. So 0, 1, 1 is our data, 0, 1, 1. So when we transmit this 0, 1, 1 and we receive 0, 1, 1, the receiver checks for even parity. That means the receiver would check if the number of ones in this is even or not. And in this case, the number of ones is even. So it counts it. There are 2 ones, it's even ones. So it accepts it as a valid code word. Now let's introduce an error. And if we introduce an error, say in the first position, the first bit is 0, we make it 1. So the first bit has changed. And the second and third bit are correct. So the first bit we have introduced an error here. So the receiver will check for the parity and see if it is having an even number of ones. And obviously the number of ones here is 3, which is odd, and therefore the receiver would say there is a problem with this code word and detect the error. So it detects the error. Detects error. No problem. And suppose we introduce 2 errors in this. So let's say the first bit 0 became 1, the second bit, which is 1, became 0, and the third bit is correct. So there is an error in the first position, there is an error in the second position. However, in this case with 2-bit errors, the receiver or the decoder will check if the number of ones is even. So because we used even parity for our communication. So when it checks it, it finds that the number of ones is even, and therefore it thinks that there is no error. So it thinks that there is no error, so it fails to detect the errors, right? And when we introduce 3 errors, let's say the first bit, which is 0, became 1, the second bit, which is 1, became 0, and the third bit, which is a 1, also became 0. So in this case now all 3 are erroneous. So there are errors in all 3 positions, and the receiver can check for the number of ones, and if it checks the number of ones, it expects it to be 1 because we used even parity, but in this case there is only 1 1, which is odd. Therefore it detects the error. So in this case detects the error, right? However, it does not know how many errors are there. Whether it is this case or this case, it can only detect the error, but it doesn't know how many errors are there. It doesn't know that all three are wrong or only one of them is wrong, and it also doesn't know which of the bits are wrong. Okay, it can know that there is some error. That means it can detect the error, but it cannot correct the error even when it has detected it, right? But when there are even number of errors, it cannot even detect the error. It thinks that the received code word is a correct code word, a valid code word, and therefore it does not even detect that error. Okay, so parity codes have a limitation that they can detect only odd number of errors. If the number of errors is even, it does not detect it. It thinks it's a correct code word and accepts it as a valid code word, so it would fail to detect the error. And even if it can detect it, it cannot correct it because it does not know, or the coding scheme does not know which position has been corrupted, whether it is bit number 1 is corrupted or bit number 2 is corrupted or bit number 3 is corrupted, because the receiver does not see what you transmitted. It only sees what it received. And by looking at the received code word and by following the rule that it has to be even number of ones, it checks it and finds that the number of ones is not even in this case, and therefore it knows that there is a problem. But it does not know where the problem is, whether the problem is bit number 1 or bit number 2 or bit number 3. Which one has changed, it cannot detect it, right? Or it cannot even know whether more than one has changed. So the parity code can only detect odd number of errors, but it cannot correct any errors. And in the case of even number of errors, it cannot even detect them. Okay. Now what we're going to do is we'll extend the idea to developing a code and discussing about a code which can detect as well as correct the errors, and that code is called as a Hamming code. So we're going to talk about Hamming code. Okay, and again, Hamming codes can be designed with various code rates, but in this particular case we are going to talk about 7/4 Hamming code. Okay, Hamming code 7/4. Okay, that means n is 7, the block length is 7, and the number of information bits is 4. That means we are going to have 4 information bits, and to 4 information bits we are going to add 3 parity bits, so the total code word length becomes 7. So number of information or data bits k is equal to 4. Number of parity bits, which is n minus k, which is 7 minus 4, that means 3. So that means we are going to take 4 bits at a time, 4 information bits, and for 4 information bits we are going to add 3 bits according to some rule, and the total block of 7 bits will be transmitted. So for every 4 bits we are going to add 3 bits of parity or 3 protection bits. So the code word length, or we call it as the block length, n is equal to 7, right? So what is the code rate in this case? Let me write that a bit clearly. Code rate R is equal to k by n, which is 4 by 7. Okay, so 4 by 7 will give you a certain coding efficiency, which is just over 50%, right? 4 by 7 means it will be around over 50%. Okay, so for every 4 bits we are adding 3 bits of parity. So the code rate is 4 by 7, and that accounts to a coding efficiency of a little over 50%. Okay, now the question is, how do we compute the parity bits? For every 4 information bits we are going to add 3 bits. How do we know what are the values of those 3 bits? Okay, that is computed according to some rule. So first of all, with 4 information bits, how many possible messages are there? There are 16 possible messages. With 4 information bits, there are 16 possible information bits, right? The information combinations. So with 4 bits of information, 16 possible messages are present. That means for each message we are going to create a code word by adding 3 parity bits. So we will create a code word for each message. For each message, and so therefore we are going to produce 16 code words. Okay, so what are the information bits? The information bits are going to be 0 0 0 0 0 0 0 1 0 0 1 0 and so on up to 1 1 1 1. So we have totally 16 messages, and for the 16 messages we will create corresponding code words. So 0 0 0 0, and we'll add 1 2 3 bits of parity. 0 0 0 1, and we'll add 3 bits of parity. 0 0 1 0 and 3 bits of parity, and so on up to 1 1 1 1 and 3 bits of parity. The question now is, how do we compute the 3 parity bits? So to do that, the 7/4 Hamming code generates the code words by using what is called as a generator matrix. So it has what is called as a generator matrix for 7/4 Hamming code. So what we do is we take these message bits and multiply the message bits with the generator matrix. That will produce us the code word. So let us see what the generator matrix looks like for the 7/4 Hamming code. So the generator matrix we denote it as G, and it is of the form 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So if you notice this part of the matrix, it is an identity matrix, right? So it has ones along the diagonal. So it has ones along the diagonal, and everything else is 0. So it's basically an identity matrix. So the first part of the matrix is an identity matrix, and then we have a second part which is 1 1 1 1 0 1 1 1 0 and 0 1 1. So that's the second part of the matrix. If you notice now, this matrix has 7 columns: 1 2 3 4 5 6 7. Why? Because we want to create a code word of length 7. So it has 7 columns and it has 4 rows. The 4 rows because the information bits is having a length of 4. Each message is having a length 4. So there is 4 rows. Only then we can multiply these two, right? We can multiply the message bits with the generator matrix only if the number of columns here and the number of rows in this are identical. So we have 4 columns in the message vector, and the generator matrix has 4 rows, and the generator matrix also has 7 columns because we need to produce a code word of length 7. Okay, so how do we produce the code words? We are going to produce the code words by multiplying each message with this generator matrix and that will give us what is a code word. So I'm going to illustrate to you how to produce some of the code words. I'm not going to do for all the 16. I will do for 2 or 3 of these messages, and then you can work it out yourself, and it's also present in the notes, so you can see all the code words being calculated in the notes. But in the lecture, in this video, I'm going to do only for the first 2 or 3 messages. Okay, so let's take the first message, which is 0 0 0 0 0 0 0 0. That's our message, and we want to multiply that with the generator matrix. So what is the generator matrix here? 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and we have 1 1 1 1 0 1 1 1 0 and 0 1 1. Okay, so we are going to multiply this, and again let me just put a red line here, a dotted line, just to show that this matrix is having 2 parts, right? So the first part of the matrix is basically an identity matrix of size 4. So we are dealing with a 7-4 code, so it's an NK code, right? NK 7 4. So N is 7, K is 4. So the identity matrix, which is the first part of the generator matrix, so identity matrix will denote it as I, and it has a size of 4. It's a 4 by 4 identity matrix, and in this case the 4 represents the number of information bits, which is the K, and this part is called as the parity matrix, or we denote it as P. And what is the number of vectors here? Number of columns is 3. So it is, we are going to add n minus k, 3 parity bits, right? 7 minus 4, which is 3 parity bits that we are going to add. So in general, we divide the generator matrix into 2 parts as ik and pn minus k. So that's the identity matrix, and pn minus k is the parity matrix. So the generator matrix is a combination of these 2 matrices. Okay, so now we multiply the message with the generator matrix. So it is multiply the first bit with the first position here. So that's 0 into 1 plus 0 into the 0 plus 0 into 0 plus 0 into 0. So it's 0 plus 0 plus 0 plus 0 becomes 0. So the first bit that you get, so when you multiply this, that's equal to the first position is 0. Then multiply it with the second column. So you multiply this row with the first column, element by element, and add those values, and you get some answer. That value is what goes here. And then you multiply this row with the second column of the generator matrix. So that's 0 into 0 plus 0 into 1 plus 0 into 0 plus 0 into 0. Again, that's going to be 0, because we have all zeros here. It's all going to be multiplied, and when you add them, you're going to get 0, right? So 0 into 0 plus 0 into 0 plus 0 into 0, 1 plus 0 into 0. So 0 is multiplied with anything is going to be 0. So the code word that you're going to get is just 0 0 0 0 0 0 0. So for the message 0 0 0 0, the code word you're going to get, I'm going to write it here. The code, I'll write the parity bits in a different color. So the parity bits you're getting here is 0 0 0. So that's the message, and that's the code word. Now let's do it for the second message, which is 0 0 0 1. So let me just erase this and write a 1 there. Let me change my ink. So 0 0 0 1, and we will make the computation again. So I'm going to erase this. So now when we multiply 0, 0, 0, 1 with the generator matrix, what do we get? So it's 0 into 1, which is 0, 0 into 0, plus 0 into 0, plus 1 into 0. So it's all 0. 0 plus 0 plus 0 plus 0 will become 0. Again, for the second one, it is 0 into 0, 0 into 1 is also 0, 0 into 0 is also 0, 1 into 0 is also 0. So that also you will get it as 0. And just to speed up things, if you notice, this is the identity matrix, right? The first half of the matrix, or the first part of the generator matrix, is an identity matrix. And identity matrix means like the number 1, right? If you multiply anything with number 1, 4 into 1 is 4, x into 1 is x, right? So if you multiply this vector with this matrix, you will get the same thing. So the first 4 bits are always going to be the same as the message bits. So henceforth, when I do subsequent examples, so the first 4 bits you need not calculate directly because this is an identity matrix. So multiplying this message sequence with this IK will produce the same sequence, right? So we'll just write it. What will differ is only the parity bits, that is the multiplication of this with these 3 columns. So that is what we are going to compute. Okay, so we'll just write them directly 0, 0, 0, 1. So the multiplication up to here is finished. So now we multiply this row vector with this column vector. So it is 0 into 1, which is 0, 0 into 1 is also 0, so 0 plus 0, the third one is 0 into 1 is also 0, so 0 plus 0 plus 0, and the last one is also 0, because 1 into 0 is 0, so we add 4 zeros, it becomes 0. Then with the 6th column now, 0 into 1 is 0, 0 into 0 is 0, 0 into 1 is also 0, and 1 into 1 is 1. So you're adding 0 plus 0 plus 0 plus 1, right? So when you multiply this with this vector, so you get 0 into 0, 0 into 1 is 0, 0 into 0 is 0, so that's 0 plus 0, 0 into 1 is 0, that's 3 zeros, plus 1 into 1 is 1. So when you add it, you get, I'll do the calculations at the bottom here. So let me put the calculations somewhere on the side here. So I'll do the calculations at the bottom here. And so we get 0 plus 0 plus 0 plus 1, which is equal to 1. So we'll write it as 1. Okay. And the last one would be 0 into 1 is 0, so that's 0. The next one is 0, the second bit here with the second position here, 0 into 1 is again 0, so that's plus 0. The third one is 0 into 0 is also 0, so that's plus 0. And the last one is 1 into 1 is 1, so that's plus 1, so we get it as 1. So that's 1. So we have the 4 information bits as it is, 0, 0, 0, 1, and the 3 parity bits are 0, 1, 1. So the message 0, 0, 0, 1 gets converted to a code word which is given by this whole thing. The 3 parity bits that we have here are 0, 1, 1. So let's go back and write those parity bits, which is 0, 1, 1. So for the second one, we have the parity bits which are 0, 1, 1. Let's do it for the third message, which is 0, 0, 0, 1, 0, and we'll compute it. And before I go into that calculation, I just want to emphasize here that the addition that we are doing over here is not normal addition, it is basically modulo 2 additions. Okay, so I'm going to put a circle. Oh. So let me close the bracket and just to illustrate. Okay, this is modulo 2 addition or the XOR operator, right? So this addition is modulo 2. So that means if the sum that you get here is an odd number, you will put the value as 1. If it's an even number, say 2, 4, when you add it, if you get 2, 4, 6, whatever, if it's even number, then the corresponding bit is 0. If it is odd number, then the corresponding bit will be 1, right? So in this case it's 1, which is an odd number, so the corresponding bit is 1, right? So similarly, we will now do for the next message, which is 0010. So I'm just going to erase this bits and I'll erase the code word as well, and we'll make the computation again for the, and I'll erase these calculations as well. Okay, so our next message is 0010. So now again, when we multiply the message with the generator matrix, the first 4 bits are going to be the same because we are multiplying this vector with the identity matrix, so that will remain unchanged. 0 0 1 0, we'll get the first 4 as it is. Now the last 3 is what we need to compute, so we need to multiply this vector with the 5th column vector here. So 0 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0. So 0 into 1, the first one is 0, plus 0 into 1 is 0, again it's modulo 2, plus 1 into 1 is 1, plus 0 into 0 is 0, so we get it as 1. So that means the parity bit that we have here, the first parity bit is that's 1, so the first parity bit is 1. Okay, and now we multiply this vector with this part of the matrix, with this vector, this column of the matrix. So 0 into 1, which is 0, plus 0 into 0 is also 0, 1 into 1 is 1, and 0 into 1 is also 1, is 0. Okay, so let me write that. It's 0 modulo 2 addition. 0 into 1 is 0, 0 into 0 is also 0, plus 1 into 1 is 1, plus 0 into 1 is 0, so we get a 1. So it's an odd number, therefore the corresponding bit is 1. Odd number means 1, even number means 0 in modulo 2 addition, right? And for the last part, or for the last bit, parity bit, we multiply this message with the last column of the generator matrix. So it is the 0 into 1, which is 0, 0 into 1 also 0, so that's 0 plus 0, 1 into 0 is 0, and 0 into 1 is also 0, so it's 0 plus 0 plus 0 plus 0. Okay, so the 0 plus 0 plus 0 plus 0, which is 0. So the parity bits that we have here is 0 0 1 0 1 1 0. So let's go back and fill this. So the parity bits that we have for 0 0 1 0 is 1 1 0. So that makes it the complete code word, 0 0 1 0 1 1 0. Right, next we'll do it for one more. So let's say I'm going to add here 0 0. Okay, let me change the color. The next one also I'll do it 0 0 1 1. Okay, and for 0 0 1 1 0 0 1 1, what are the parity bits? Let's calculate. So let me erase this and make it as a 1. So 0 0 1 1, we multiply with the generator matrix and we have to find the code word. So we need to erase this. We'll compute the code word again from scratch, and to illustrate the calculations I'm going to erase this as well. Okay, but remember that the additions that you do here are modulo 2 addition, or in electronics terms it is the XOR operation, right? So again, when we multiply this, the first 4 bits are going to be the same for the code word, because the first part of the generator matrix is the identity. So it will be 0 0 1 1, and now we have to multiply with the parity matrix. So this message with this column. So it's 0 into 1 is 0, 0 into 1 is also 0, 1 into 1 is 1, and 1 into 0 is 0. So you get 0 plus 0 plus 1 into 1 is 1, plus 1 into 0 is 0, which is equal to 1, and therefore it is 1. Right? Let's do it for the 6th column now, right? So this is 0 into 1. 0 into 1 is 0, so we write the 0. Modulo 2 addition. 0 into 0 is also 0, plus 1 into 1 is 1, plus 1, plus the last bit is a 1 into 1 is also a 1. So the modulo 2 addition will give you 0, because when we do modulo 2 addition, we take the remainder after dividing by 2. So the total answer here is 2. When you divide 2 by 2 and take the remainder is 0, right? So 2, which is even number, even means 0. So the corresponding bit here is 0. Okay. So if the addition comes out to be an even number, the corresponding bit would be 0. If the addition turns out to be an odd number, the corresponding bit will be 1. So since it's 2 now, so the bit that you get here is a 0. And for the last one, it's 0 into 1, which is 0, plus 0 into 1, which is also 0, plus 0, plus 1 into 0, which is also 0. So it's 0, plus the last one is 1 into 1 is 1, plus 1. So that's 0 plus 0 plus 0 plus 1 is 1, odd number, therefore it's 1. So the code word that we get is 0011101. So let's write the parity bits and the code word and make the code word. So the parity bits that we get for 0011 is 101, and like this you can compute the code words for all the 16 different messages. Okay, so I'm not going to do for all the 16 messages. I'll leave it as an exercise for you, but you know the general principle. Okay, so don't be wasting your time calculating for the first 4 bits, because the first part of the matrix is the identity matrix. So when you multiply any vector with an identity matrix, you will get back the same vector. So the first 4 bits are going to be the same as your message. It's only the 3 parity bits at the end that will vary from message to message. Okay, so you need to compute the 3 parity bits, and just remember that you just multiply it bit by bit and then add them together, and if the sum is odd, you put the bit value as 1. If the sum is even, you put the bit value as 0. Okay, or that's equivalent to modulo 2 addition, or that's also equivalent to the XOR operation. Okay, so this process of producing the code words from the messages is called as encoding process. Okay, we call this as encoding. Encoding is the process of generating code words from messages. Generating code words from messages, and this is what happens at the transmitter side. So before transmitting your data, we do some encoding for protecting the information bits, so that when the bits get corrupted by channel noise, the receiver should be able to detect the errors and correct the errors, of course within some limitations. There will be some limit as to how many errors it can detect and how many errors it can correct. So every code has some limitation to it. Okay, and coding techniques that are used in modern day communications are quite complex and advanced, but what we are seeing in this course are some very basic and elementary types of coding techniques, but they are the foundation blocks of studying coding theory. Okay, so it's important in that sense, right? But compared to what we use in modern day communication systems, these are much easier and trivial, and their capabilities are also very limited compared to the capabilities of the coding techniques that are used in modern day communication systems. Okay, so we produce the code words by multiplying the messages with the generator matrix, and that produces the code word, and this process of producing the code words is called as encoding, and encoding is a process done at the transmitter side. Okay, the reverse process, which is called as decoding, we will talk about that in the next lecture, that is done at the receiver side. So the job of the decoder is to look at the received code word and then do some processing to identify that whether this received code word is having any errors or not, and then if it has some errors, it should correct those errors, of course within its capability. Okay, if there are 1 or 2 errors, maybe it can correct or detect. If there is too many errors, it may not be able to detect or correct them, right? So that depends on the capability of the code. For the 7/4 Hamming code, we will see in the next lecture what is the decoding procedure and what is the limitation, and in the sense that how many errors it can detect and how many errors it can correct, and we'll talk about those things in the next lecture. Okay, we will stop here for today. So what you're seeing today is a slightly more advanced topic than the parity codes. The parity codes that we saw earlier were just error detection codes, which can only detect errors, and that too they can detect only odd number of errors. If there are even number of errors, it will fail to detect those errors. Now we have seen today how to construct the code words for a 7/4 Hamming code using a generator matrix for the 7/4 Hamming code. Okay, in the next lecture we'll talk about how to decode it and how to detect if there is any error, and then also correct it. So what we will do is we will deliberately introduce an error in some bit position, and then we will see if that mechanism is able to detect the error, and then we will also see how to correct the error. Okay, and we will also see later on where that the 74 Hamming code has a limitation as to how many errors it can detect and correct. If the number of errors in the code word exceeds that limit, it will not be able to detect and correct the errors. Okay, so we'll discuss all of that in the next lecture. That's it for today, right? If you have any questions, we can discuss it after the video ends. Okay, thank you.